Hello guys, welcome to this lesson. In this lesson, we are going to look at nuclear stability. Nuclear stability, the factors that affect the stability of a nuclide or that account for stability of a nuclide. We have one, the neutron to proton ratio. We've talked about half-life. In this lesson, we are going to talk about the neutron-proton ratio. The neutron-proton ratio. As the name suggests, the neutron-proton ratio, it is just the ratio between the number of protons and the number of neutrons in the nucleus of an atom. If an element or an atom has equal number of protons and equal number of neutrons, its ratio becomes 1. It's equal to 1. Is that okay? So if an element has equal number of protons and equal number of neutrons, in the ratio, it is equal to 1. For example, if an element has 10 protons and 10 neutrons, the neutrons to proton ratio here becomes 10:10, or 10/10, which is equal to what? 1. Is that okay? So for stability of a nuclide or a nucleus or an element in terms of the neutron to proton ratio, we say that if the neutron proton ratio is equal to 1, it indicates stability. If the neutron to proton ratio within the nucleus of an atom is equal to 1, it indicates that that nuclide or that element is stable. Is that okay? That is a neutron-proton ratio. But I have some simple notes here on the board. Let's go through. With the first point, I said it is a number of protons. That is, we are just reviewing the definition of the neutron-to-proton ratio. It is the number of protons to the number of neutrons in the nucleus of an atom. That is the neutron-proton ratio. Nuclides with neutron-proton ratio equal to 1. So if the ratio between the protons and neutrons in the nucleus of that atom is equal to 1, it indicates that that nuclide is stable. So are stable. That is, they have equal number of protons and neutrons. Or we can say that the number of neutrons is equal to the number of protons. That is, capital N is equal to capital Z. Is that okay? So for stability within the nuclide, we talk about the neutron to proton ratio to be equal to 1. If the number of neutrons and number of protons are the same in the nucleus of the atom, it means that that atom or that nuclide is stable. You get a point here? Alright. Now another point here is that usually unstable nuclide, for elements that are unstable, that is the radioactive elements, particularly, they have neutron numbers to be greater than the proton numbers. So ideally, once we are moving from hydrogen, helium, lithium, beryllium, in that order, once we are increasing atomic number, the mass numbers also increase. And once the mass number is increasing, the number of neutrons in the nucleus of the atom also increases. So basically, for the radioactive elements, they have more number of neutrons to the protons in the nucleus. And we know that for stability to occur, we should have equal number of protons and equal number of neutrons, giving us a ratio of 1. But if the mass number exceeds the proton number, it means that the ratio won't be equal to 1. Is that okay? The ratio will be more than 1. So in order to attain stability, most elements undergo decay. So we have the alpha decay or alpha emission, we have the beta decay or beta emission. Other elements undergo gamma decay. Why all this decay? They undergo this decay to enable them attain stability or to edge them closer to stability. Is that okay? So for elements that are unstable, they tend to have more neutrons than their protons. Is that okay? And once that happens, the proton to neutron ratio of 1 that we need, we can't get that value. And it indicates instability. So they are unstable. Is that okay? Another point we also need to know is that basically elements beyond bismuth, that is, bismuth has a proton number of 83 and a neutron of 123. All isotopes are unstable and radioactive. They are all unstable and they are also radioactive. So to indicate stability of a nuclide, once you're talking about the neutron to proton ratio, the ratio should be equal to 1. Once it is exactly equal to 1, it indicates stability. So if when you take the first 20 elements, the stable elements there should have a neutron to proton ratio to be equal to 1 or slightly above 1.0. Is that okay? So those that have their neutron to proton ratio more than 1.0, they tend to undergo decay. Some undergo alpha decay to enable them to edge towards stability. Some undergo beta decay to enable them edge towards stability. That is when you are considering the band of stability. Is that okay? And there will be a lesson on that as well. Now I have some simplified rules in predicting stability. Some simplified rules in predicting stability. Is that okay? So rule number 1, we said nuclei that contain 2, 8, 20, 28, 50, 82, and 126 protons or neutrons are generally more stable. So if a nuclide has 2 protons or it has 2 neutrons, it is stable. If it is 8, any of these numbers, for their protons and neutrons, it indicates stability. Is that okay? We call these numbers the magic numbers. We call these numbers the magic numbers. We call these numbers the magic numbers. Nuclides with these magic numbers corresponds. They corresponds to the filled nuclear shells. They corresponds to the filled nuclear shells, which is similar to the electron shells in an atom. They corresponds to the filled nuclear shells, which is similar to the electron shell in an atom. It basically comes from the ideology of the nuclear shell theory. Is that okay? Please, are we there? So when a nucleus has a magic number of protons and neutrons, the nuclear force within the nucleus is particularly arranged in a stable configuration. The nuclear force within the nucleus is particularly arranged in a stable configuration, which brings about the overall stability of the nuclide. Is that okay? So this magic numbers corresponds to the filling nuclear shells. It corresponds to the filling nuclear shells. And nucleus with these magic numbers tend to have the nuclear force attraction in the nucleus arranged in a stable manner. Is that okay? Which indicates stability of that nucleus. So in addition to that, I said these are called the magic numbers, and also it indicates the stability of the nuclei. So if you want to know whether a nucleus or a nuclide is stable, we can look at those with these magic numbers corresponding to their protons and their number of neutrons. Is that okay? Don't forget, I said this magic numbers corresponds to what? It corresponds to the filling nuclear shells, which is similar to the electron shell in an atom. And in addition to that, I also said that nucleus with protons and neutrons with magic numbers tend to do what? Nucleus with protons and neutrons with magic numbers tend to do what? So I said the nuclear forces in that nucleus will then be arranged. The nuclear forces in that nucleus will then be arranged in a particularly stable manner, which indicates the overall stability of that nucleus. Is that okay? So that is it for magic numbers and the nuclear shell ideology. Alright, another rule we can use to predict is all isotopes of elements with atomic number, all isotopes of elements with atomic numbers higher than 83 are unstable and radioactive. So that is a point we can draw. So that is element beyond bismuth. That is atomic number 23 or proton of 23. They are all unstable. They have heavy masses. They have more neutrons than their protons. So there is instability in the nucleus. So for them to be able to be stable, they undergo decay. Some undergo alpha decay, some undergo beta decay. Some capture electron to convert it. Is that okay? Please, are we good? Alright. Now the last rule. Nuclei with even numbers of both protons and neutrons are generally more stable than those with odd numbers. So when I take a nucleus of an atom, and the number of protons is an even number, and the number of neutrons is an even number, we are saying that nucleus or a nucleon with even numbers corresponding to their protons and neutrons, they are more stable. And why? Why are they more stable than those with odd numbers? Why are they more stable than those with odd numbers? Simply, this is due to the pairing effect in the nuclear structure. This is due to the pairing effect. So the ideology here, or the phenomenon here, is the pairing effect in the nuclear structure. This is due to the pairing effect in the nuclear structure. This phenomenon is closely related to magic number and the filling nuclear shell. Is closely related to the magic number and the filling nuclear shell. Is that okay? So we are saying that those with even number of protons and neutrons, they tend to pair up in energy levels within the nucleus of that atom, which brings about stability. But those with odd numbers of protons and neutrons, they have unpaired nucleons. They have unpaired nucleons, which indicates instability of that nuclei. So we can use these three basic rules to indicate stability of a nuclei. Once we're talking about the neutron to the proton ratio of that nuclide or the nucleus in question. Is that okay? All right. Thank you.